Intel. So this is the second Intel talk in this session. So this is the outline what I'm going to talk about. First, I will try to motivate why we start this project, and then talk about this project called GDPI. And if time allows, I will spend some time on how we implement it, and then we want to show you some experimental results to show you that it is something that's really interesting, and then finally talk about the release plan, and hopefully we can get some discussion after the talk. So I think many of you here knows about NumPy. So it is a very great package in Python. So probably one of the most useful package. And I think the point here is NumPy has been putting a lot of efforts on improving the performance. So many of them, the function calls are already implemented in C. So thereby approaching native performance. So that is good. However, at the same time, as Python and NumPy is increasingly used in more compute-intense application domains like machine learning, image processing, or computational finance, so there are more higher demand on performance. So as a result, even the native C performance in NumPy is becoming not good enough. So people have started accelerating NumPy codes with different what we call the hardware accelerators, like the multicore CPUs, GPUs, or FPGAs. So let's look at the current approaches to accelerating NumPy. So there are many existing work, so it's hard to summarize all of them in one slide, but I'm trying to classify them into three approaches. The first one is you can write the accelerator parts in C and then link the compile code, statically compile code with the Python program. So a very good example is SciPy. And the second approach, I would say it is, you can add some annotations to mark the parts in the Python program that you want to accelerate, and then use a just-in-time compiler to compile those parts. And I think the good examples of this is the NumPy for the CPU part, and the Hope, which is a presentation that that made early today, and PowerKit and PyFriend. And then the third approach is you can write the accelerated parts in another language, and which are embedded in the Python program. And I classify PyCUDA, PyOpenCL, and even Number for GPU as this approach. So I guess because many of you are more familiar with the Number, so I will try to explain why I think the Number for GPU approach is less than decide at this point. So because I think that the second approach, which is you add annotations, that is, I think, the approach that I like the most, and I think for most users, that probably is the easiest to use. But unfortunately, this system currently don't work on GPUs of FPGAs. So if we look at the current numbers GPU support, I think there are two main concerns. The first one is hardware specific. So they have been supporting NVIDIA's CUDA for a few years, and recently they announced the support of AMD's HSA. However, they don't have any other support for GPU. I'm from Intel, so of course I care about Intel GPU. But other than that, they don't have support for ARM. So if you have an iPad, you want to accelerate on iPad, you cannot do that. And programming challenges, CUDA and HSA's versions are incompatible. So you cannot run a number CUDA program and then run it on AMD GPU. So they are incompatible. So that means if you, as a programmer, if you want to have a number program to run on different GPUs, you have to write multiple times. And if you look at the program model, the GPU, they choose an explicit GPU programming model, especially in the CUDA versions. So for example, you have to write the data, the code to transfer data between CPU and GPU. So I think if you are a GPU programmer, you will be happy doing that. But if you're a typical Python programmer, I don't think you want to do that. So let me give you a CUDA's numbers CUDA example. So this is, I think I got it from their website, and this is a code to do the manual blocks in CUDA. So if you look at all the red things, the code that you have to add for doing CUDA. So those are pretty GPU-specific things, so you do need to understand GPU a little bit. And also, if you want to move to like ARM GPU, this thing won't work because ARM doesn't support CUDA. So the motivation here is we want to build something that you write, the program runs once, and then work on every GPU, every CPU, and even FPGA. That's our goal. Just to explain why I call this project GTPy, because internally, GT means graphics in Intel, and this is motivated by we want to support Intel graphics. But fortunately, we're able to find some meaning for GT because GT also means green tree Python, so which is shown here. So that is, but this is an afterthought, I mean, to be honest. So our goal is we want to provide a system to accelerate NumPy code that is easy to program and yet can run efficiently on a variety of hardware. So we decided to use a familiar programming model, and as I'll show you, we adopt something like OpenMP-like annotations to annotate a program. And then we want to be able to achieve our ultimate or dream goal, which is one program for all accelerators, including multicore CPU, GPU, and FPGA. And looking at that, it seems that OpenCL is the one that works on all these platforms. So we decided to generate OpenCL code. And then we want to generate highly efficient code. So like other project, we use a just-in-time approach plus some domain-specific optimizations that we are going to do later. So this is an example of this is of course a toy example, but I cannot explain a very complex example in a few minutes. So, but this is on the left-hand side, or yeah, on your left-hand side, it's the original Python program to compute the value of pi. So basically, the main computation is happening in the for loop. So you make use of NumPy, and then you write the program run nicely. You see that there's some optimization opportunity here, which is the for loop. First, it is actually embarrassingly parallel for loop. So if somehow you can run each iteration of the for loop in parallel, then you gain performance. But how will you do that? So in GTPy, we provide you some way to say, I want to run this for loop in parallel. And the way to say that is you mark this as a pragma, which is actually for a normal Python compiler or interpreter, is a command. So a pragma, say it's a GTPy, and then you say it's a parallel loop. That means the compiler is free to parallelize it. And then you say, I want to run it on GPU. So the target is GPU. So by doing that, my system will automatically run this code on any GPU that I know of. So the usage model, just to give you some high-level overview of the usage model. So GTPy can accelerate 3 types of regions: loops, which is very common. So of course, we want to accelerate it, and you can accelerate less loop. Or you can accelerate vectorized call, which is known as universal functions in NumPy. Or you can accelerate certain library function calls. And then you can specify which hardware target platform you want to run on. Currently, you can run it on the CPU sequentially, 0, or you can run parallel, which is run on the CPU in parallel, or you can run on the GPU, in parallel. And we support common Python and NumPy functions in the regions that you accelerate. And because GTPy pragmas are actually commands, so it could be ignored by regular Python interpreters. So if you want to develop a program, so that would be pretty helpful, because initially you can, if you have a GTPy program, but it's a pragma, so for other non-GTPy compiler, it's just ignore it, but your program should still run correctly. And then you fit it into GTPy, and then it get a optimized run. So I would like to go through some examples to illustrate these different usages. So the first one is the accelerated loops with calls inside. So here, so this is a loop, and then you call foo twice. So if you say pragma GTPy parallel loop target GPU, then you will get some speed up. And the second example is, now you have a nested loop for Y and for X. Then you have 2 choices here. You can parallelize the outermost loop, or you can parallelize the two loop, I mean, the nested loop. So we allow you to specify that. And actually this, you say, pragma GDPI parallel loop collapse, and then you specify two. That means you want to collapse the two loops into one. And this is actually not something that I invent. It's based on OpenMP collapse semantics. So currently, we try to use OpenMP semantics to guide us to how to let user to specify the parallelism. So another example is you could accelerate vectorized call. So in this example, again, you say, so you have a two dimensional matrix, MAT. So number of rows, number of columns. So suppose that you want to do some computation, you loop over each column, and then for each iteration, you apply it on the entire row. So it's basically a vector. So in NumPy, you can use this universal function to say call fun, and then you pass the entire vector, and then you perform the operation on the entire vector. So in this case, you can say, I want to vectorize this function. I say, I want to use GDPI to vectorize this function. By doing that, then, when you execute this loop, then the function will be vectorized on the GPU. So, and then the final usage model is, suppose that you have some heavyweight function call. For example, if for NumPy, you want to use the random number generator to get a random number from the normal distribution. So we provide some accelerated version of those libraries. So you can specify that, oh, I want to replace I want to replace this NumPy library by the GDPI version to run on the GPU. And by doing that, then you can get the accelerated version. So far, I talked about the motivation and then the usage model, what GDPI is. Then I will spend some time on the implementation. So basically, the compilations has three main steps. The first one is function outlying. The second one is type inference. And the third one is cogeneration. And I will use the earlier Pi example to illustrate this step in the next few slides. So just to remind you that that is the NumPy, that's the GDPI program for the computing the value of pi. So the first step is function outlying. So what it does is, remember that we use a pragma to mark the for loop. So in this example, so the first thing that is we need to extract the for loop as a function itself for our analysis. So you see that we extract the for loop into a function called region 0_10. And the key here is when we extract the function, we also extract the arguments, the input arguments to this loop body, to this function, which are n, step, and result. So by knowing that, with this very important that we know about these arguments, because we need, as you see, that we need to add some runtime type check on this argument, which is shown here. The next step, which is, type inference. So at the runtime, we add more code, the JIT, add some code that you see that here, we dynamically check the type of n, step, and result. So we call this Python function type to get the type. And then we pass this type to a function that GDPI create, which is doing a dynamic type inference. And after this type inference, we get all the variables inside the function, the types of all the variables inside the function. So now, after the type inference, I know that, okay, n is integer type, step is float, the result is a float await, and then I is in, and x is float. So now, after these two steps, we get a function outlined, and then a type inference. So now we are ready to do cogeneration, which is step 3. So from the AST, and the type, which is the abstract syntax tree of the Python of the region that we compile. And then from the type information, then we can generate first, because in OpenCL, there are two parts. One is the host program, one is the device program. The host is run on the CPU, and the device program is runs on the device that you use, either GPU, FPGA, or CPU. So we have to generate two programs. So GDPI will automatically generate the host program and the device program from the region, which is shown here. So you see now, when you run, it will automatically run the host program, and then the host program will automatically launch the device program on the device. And as other JIT, we use code caching to avoid recompilation whenever possible. So now, let me show you some experimental results. So we run, our main results is we run a number of benchmarks, X benchmark on Intel CPU and GPU. And our baseline is the Intel Python 2.7, which is what just Anton presented. The benchmark, we use black source, heat diffusion, Mandelbrot factor, matrix multiply, multicore option pricing, 2D stencil, and body and ray tracing. So those benchmarks, mostly I collect from the web, and I got some from the number as an example site, and also from some from institute, like ray tracing. I think I got it from MIT. So all the measurement that I'm going to show is measured in the second run. So that means the JIT code is already in the cache. So I didn't show you the JITting overhead, but the compilation overhead. But our experience is that usually the compilation of the host, the OpenCL compiler, is usually around 0.6 seconds to 1 second. So this is the speed up over the Intel Python 2.7. The y-axis is the speed up. So that means 1 is the Intel Python speed. And you see that I need to use the log scale because some speed up is too large to show in a linear scale. And then you see for each benchmark, there are two cases. The blue is if I schedule or run it on the multicore CPU, that's speed up I can get. And then the red is if I run on the Intel GPU, how much speed up I get. And in each case, it is the same program. I just have to select the target, whether it's run on CPU and GPU, then you get the result. So there's no program change. So on the left-hand side, this is a minor speed up. You get something like 1.5, 1.6. But on the very end, ray trace, you got over 10,000x speed up. So I guess the question that everyone will ask is why is there a big or large discrepancy in the speed up? And the reason is, it really depends on how good the base case is. For something like Monte Carlo and heat diffuse, the NumPy code, remember that they're already mostly executed in native. So that means the speed up that GDPI can provide is mainly from parallelization and vectorization. But on the right-hand side, to the other extreme, from Mandelbrot to ray trace, the NumPy code, even the NumPy code itself is still largely interpreted because the expressions is so complicated that there's no way for NumPy to execute all of them in native C. So for the right-hand side, we are getting the speed up from three sources: native execution, parallelization, and vectorization. And then I did some experiment to show you the results on other GPUs. So the other GPUs that I have, like NVIDIA and AMD GPUs that I have in my lab are pretty old. So hardware-wise, they are not really a high-performance one in today's standard. But I just want to demonstrate that you just have the same. You can just use the same program, same GDPI program, and then you will also run on different GPUs. So that means you write the program runs, and then if you get a more powerful CPU, GPU, then just run it, and then you get the performance automatically. So in terms of the plan, I'm currently, the plan is on track to have alpha release to the public by the end of this quarter, which means September. It will be free and open source, and you can check this web page, but I don't think you can remember it, of course. Then, of course, you can simply Google GT-Pi. And then I think our next two target, actually the next one is we will add support for Intel Xeon Phi, which is an accelerator developed by Intel, which will be released to public soon. And then we are also interested in applying this to accelerate on FPGA because Intel recently acquired Altera and they have support for running OpenCL on the FPGA. So this should be pretty straightforward. So I guess let me do a summary. So we are seeing ever-increasing demand on NumPy performance, and the existing approaches to accelerating NumPy code on hardware is either too low-level or hardware-dependent. And we hope that GDPI will enable acceleration of NumPy code on CPUs and GPUs with minimal hardware-portable programming effort, but at the same time, we'll see significant performance gains. Please ask questions. Yeah, I guess.
Come September, I want to implement this. What challenges or learning curve should I expect to experience?
I think the main thing is because the question is if you want to try this after September release, then what kind of challenge or difficulties that you expect to see? So I think the main thing is this is because the project is still relatively new, so I guess there we won't be able to implement all the NumPy functions that in the accelerator region. So we'll only provide a subset of the NumPy functions. So there's some restrictions. So we need to document it, and of course, then you need to read the document. And we try to improve our error message, but I mean, as we talk to the NumPy developers, they spend a lot of time, a few years, to actually to complete the NumPy library. So there's a lot of work. So that will be something that keep in mind. So it's not, it's a first release and it will take a while to really mature. But if you follow the constraints, so I guess hopefully you can still get your things working. Yeah, please. Fork. I think your question is what happens if there's fork in the program? I don't think it will be a problem because when from the GDPI point of view, if you mark say this region is parallelizable, we actually regenerate a totally parallelized code, so we don't hold any lock. So it's all the code is just like a OpenCL program. So I don't think so. Basically, it's trying to apply multi-threading and vectorization on the process itself. So I don't think there's a special issues here based on my understanding. And your second question is, sorry, I forgot. Oh, the cat, we have our co-cache system. So our cache system is built our own. So basically, we when we generate the pragma and then the source code, we take a hash MD5 of the source program, and then when the GC, again, we compare the hash to see if it is style or not. So I don't think it's a problem. It should work, I guess. Yeah. Yeah. Yes, please. Currently, you cannot. I think, yeah, this is something that we are thinking about how to handle it. Yeah, but currently, I think you have to do it one at a time. So I don't think you can call each other. But this is something that I have been thinking how to handle it. And yeah, I think, but that's a good question. Yeah. Yes, please. No, first you notice that this is a log scale. So, like for example, I think you like the matrix multiply. So the GPU is actually is more than 2x. So it is not bad. Actually, the Intel GPU is like I think is comparable to a mid-end discrete GPU, but it's on die, so it saves more power and also it's right on your laptops and you can use it right away. So you don't need a extra graphics card. So of course, whether CPU and GPU will win, it really depends on the program nature. But for certain things, like especially if you look at this ray trace, it is a really very GPU friendly program, so it wins a lot. And I think if you run it on a state-of-the-art NVIDIA GPU, you will see even a much, like a 2x or 3x performance gain. Yes. I only compare it quantitatively at IC, but we haven't collect the performance results. But this is something that we probably should do before we release to put on the website. But I guess obviously NumPy has been around for a while, so it's much more mature. So, but we're trying to target a little bit differently, like hardware platforms. So we want to, of course, obviously provide the support for Intel GPU and also the Intel Xeon Phi. So that is something that we are more concerned about. Yes.
Is it possible to combine CPU and GPU into parallel?
Yes. I personally, actually, I did some previous research work like 6 or 7 years ago in presenting at another conference. So that is doable. But in this framework, actually, it's pretty easy. If you know the problem, you can, like the matrix multiplication, this is a good example. You can just divide the matrix into two and then ask the CPU to compute this and then other GPU compute that. So that's really doable. I think the key is how do you decide how much work you pass on to the CPU, how much work to pass to the GPU. So that's an pretty active research area. So I worked on that for a while, but then there are more recent work. But that is definitely a good area to look at.
Would it be a nested pragma?
I think you will be say like the pragma, then you say automatic distribution, something like that. Then you just let the system to take care of it. Thank you.